Yeah, welcome to lecture 25. So today's lecture is about minor losses in piping systems. Last lecture we talked about major losses piping systems, and it's called major losses because for many piping systems this is the major source of loss. The major loss is the pressure loss due to friction in a long straight pipe segment. So it's just a plain long circular section of pipe. We can calculate the major loss, the major pressure loss, do that. So that's the major loss that has to be overcome by equipment like pumps in order to transport fluids long distances. So for example, water mains like in your project. We have a couple of different methods. The hard part in major losses is calculating the friction factor. So we have a couple of different methods to do that. I recommended for hand calculations, like on an exam or homework, to use the Holland equation because it's explicit in F. But for computer calc, such as your project, you're supposed to use the Colebrook equation, which requires iteration. So tomorrow's tutorial will require a lot of calculations of friction factor. This analysis, I would say, is relatively straightforward once you do it a couple of times. So I'd really recommend that you look at homework. I'm not sure what homework number it is. The latest homework, questions 2 to 4, where I have you calculate the friction factor a bunch of different ways. So in the tutorial tomorrow, we're going to be doing that quite a bit. Also, so for the tutorial tomorrow, please bring like a laptop or something you can use Excel or Python or MATLAB or something like that on. So you'll be basically doing, for example, if I had you to calculate the pressure loss 15 different times, you wouldn't want to do that by hand, right? You'd want a nice spreadsheet that calculates it for you, where you can just vary a parameter. So that's the sort of thing we're going to be doing tomorrow. The idea of tomorrow's tutorial is to explore, say, the effect of diameter on major losses or the effect of surface roughness on major losses. So that's the sort of thing, flow rate for your project, right? And you guys get to pick the diameter. So it's good to know how the diameter affects major loss. And that's a big part of tomorrow's tutorial. So that's major losses. Today we're going to talk about minor losses. So new material. So this was the piping system I showed in the title slide. So I think some of you might not have seen a piping system like this ever before, but some of you probably have seen this on maybe co-ops. Does anyone want to point out any system components other than straight pipe in this piping system? Got some valves, right? We have lots of valves here. Anything else? Yeah, there's some gauges there. So it looks like some sort of pressure gauge there. So there's a couple of different types of valves here. This looks like a gate valve. So that's a very common type of valve in large diameter piping. This looks like a ball valve. You can generally tell valves apart by their handles. So this is like a quarter turn ball valve. So this will open completely in a quarter turn like that. So when it's like this, that's closed. And when it's like that, it's open. The gate valve takes a lot of turns to open, as any plant operator knows. So we have some other types of valves here. So these look like control valves. Does anyone know what type of control valve this is? This looks like, to me, a butterfly control valve. So what this is, it's a very thin, this whole thing here is a valve. And so there's basically a circular plate in there, and the plate just rotates. So when the plate is completely blocked the flow, it's basically stopped. When it's completely sideways, that's fully open. So these look like some sort of actuators that would be used in a control room. So this is like a remotely actuated control valve. So this system is able to be controlled remotely. Any other piping system components other than just straight pipe? There's kind of an obvious one that's going to sound obvious once I put it out. Yep, some elbows. Part where the pipe isn't straight, exactly. So we have some elbows there. There's lots of different diameters of pipe in this piping system. But yeah, in general, we have elbows. So all these different components are different than just our straight pipe section. So we need to learn how to calculate the pressure loss for them. Yep. A junction, like a T or something like that? Yeah, so there's a T up there. That's another source of major loss. Another source of major loss in this would be, this looks like some sort of drum or something mounted on you can see parts of the structure here. So there's a lot of money made in industry, just structural analysis of the sheer weight of all this metal here. So this looks like some sort of big drum filled with fluid. And there's also a pressure loss when fluid enters something like this. So sort of, we talked about entrances, but there's also exits, which that would be considered. Does anyone know the purpose of this small valve? So this is the main flow, right? This is a huge diameter pipe. What would be the purpose of this valve? Yeah.
That's just like a pressure let.
Yeah, so it's to off outlet pressure. So and say you have to maintain this equipment, you shut down all the pumps, the flow all slows down. This flow could be quite pressurized still. So if you close this gate valve and open this, you can let out some of that pressure. So it's not just a big source of stored energy. Say we have to replace this valve. Um, we could use this to basically bleed off some of that stored energy before we start undoing these. Any other questions about this piping system?
You know what this is for?
No, I don't. This is just an image I found online. So I don't know what type of fluid this is. In general, the placement of all these different system components is governed by many things. Probably the most important of which are there are many, many codes and standards for all this stuff. For example, the dimensions of all those bends, elbows, they're all standardized. Just like the wall thickness of this pipe is, the diameter of the pipe is all standardized. There's these markings. So this is a 200 pressure class valve. So all of this stuff is standardized. It's like a big engineering Lego set. Everything is standardized so that it fits together. You can a priori, so ahead of time, design all this in a computer. So if you work in this sort of industry, you will come to know these codes and standards quite well. There's also usually the company standards that govern what has to be placed where. The placement of things like these control valves, that would be decided probably by some sort of chemical engineer working in this plant that wants to have, say, control over the flow there. Or like this manifold here, it's important to be able to adjust whatever flow is going into this drum. Any other questions about this? Okay. So we're almost at the end of this section. So we're talking about minor losses. Our learning objectives for today are to understand these different piping system components, calculate the pressure drop in one of these components, convert between different types of units for pressure that are used in engineering. So those are head units and pressure units. We're going to see what that means. We're also going to see how we can use minor losses to measure flow rates. So we'll define minor losses to start. So again, these are frictional, meaning that our fluid is viscous. So frictional pressure losses. In a system component. So for example, fittings is a pretty general term. Valves, bends, entrances, exits, expansions, and contractions. So those are like reducers or expanders is the technical term for that type of component. So let's draw a picture just like we did with our major losses. So say we have pipe here coming into a valve. So this is my best impersonation here of a gate valve. So inside a gate valve, there's this big gate, just like in the name. And when you raise and lower that handle, it raises and lowers this gate to close off the flow. So this pipe continues here. So we'll consider the point, say 1. So just to be clear, these are flanges. So this would be considered like a flanged valve. Not all valves have to be attached by flanges, but like the valves we just saw there are flanged. So we'll take the point 1 and point 2 is further down the pipe. Just because I know my drawing is horrible, that's a valve, so it's labeled now. So the minor loss, again, is P1 minus P2. We call that delta P. The minor loss is equal to KL times rho V average squared over 2. Now the reason that I didn't draw point 2, so point 1 is right at the start of this valve. The reason I didn't draw point 2, say here, is because this pressure actually, say, drops due to flow interactions through this valve. So the pressure will drop, and then it slowly recovers until the flow is fully developed again. Now, this pressure drop is the unrecoverable pressure drop from this valve. So say the pressure starts here, it's going to drop quite a bit, and then it's going to slowly recover as the flow redevelops. And that pressure drop here, that's this delta P. So it's not the local pressure drop over this valve, just something to remember. So this is the pressure drop that you get in addition to the pure length of this valve. So let's just compare this equation here with the major loss equation. That was delta P equals, I'll do it in red, F L over D rho V average squared over 2. So this term in the major loss, you can see these two equations look quite similar. We still have the dynamic, sort of a dynamic pressure, rho V squared over 2 times some sort of dimensionless coefficient. So we're going to see later on that we can get the total loss by sort of just adding up these coefficients, multiplying by that. Are there any questions just about this equation or the setup for the locations of points 1 and 2? You don't have to think about the location of point 2 that much. You'll see that we basically just pretend like this is a pressure drop for this valve. Any questions about this? So a question you might have is, how do we know what KL is? In practice, KL is going to be provided by manufacturers for your different piping systems, piping system components. So KL is the loss coefficient. Again, it accounts for all irreversible energy losses caused by the fitting. Maybe I'll say component instead of fitting. How do we get KL? So the manufacturer, if you do this sort of analysis on your next co-op term or your engineering practice, I would not recommend using like the loss table that I'm going to give in this introductory fluids book. The engineers who you work with will have probably a huge book with these loss coefficient values that they use and that are much more accurate. So manufacturer/reference books. For your homework, we're going to use table 8.4 in our textbook. So I'll show you what that looks like now. So It's a 2-page wide table. So here's some entrances and inlets of piping, and it gives you the loss coefficient KL for here. We're going to talk about what alpha is next lecture. Don't worry too much about what alpha is. But you can see for turbulent flow, I guess if you spend some time looking at this, and this is posted on Learn, you can see, say, the advantages of rounding an inlet. So the loss coefficient for this, I didn't mean to draw there. Let's look at, for example, this sharp-edged inlet. Okay, this sharp-edged inlet here has a loss coefficient of 0.5. If you just round the corners of this a little bit, it goes down to well-rounded, say 0.03. So just by rounding that, you can basically eliminate the minor loss from that. Yes, please.
Is KL purely a geometrical property, or is it also based on material properties?
That's a good question. So the first question is KL purely geometric? It is not. In the real world, it depends on lots of stuff. Even in terms of geometry, for different things in this table, the KL depends on, say, the geometry. It depends on Reynolds number is a big one for the real world, but in our analysis, we're going to assume it's just Reynolds number independent. If it depends on materials, so definitely, the manufacturer will give you that because they know what material they're valving. Any other questions? Yep.
Sorry, you said so it starts at the closed component and then it goes up. The pressure gets increased again.
It recovers.
Why does the pressure recover and why is it not just drop rate?
Why doesn't it drop and stay dropped?
Yeah, like why is it like it goes?
Yeah, so the pressure across this pipe is kind of a tough thing to define. So when it's fully developed, you can assume you have a uniform pressure. But for something like this, until it's fully developed again, you get kind of a recirculation zone here, which will have a large negative pressure. So if you were to measure the pressure at the wall, it would do that. So here's some loss coefficients for entrances, exits. You can see for a sudden expansion like this, depends on the ratio of the diameters. See? And there's also some ones for bends and valves and T's and all that there. So there's some practice on the homework for how to calculate this. For your project, I have provided the loss coefficients that you need to use. So this is part of creating a level playing field so for the competition kind of part of your project. So you're not expected to go, future students in this course might be expected to do that, to go and look for their own valves. Because if you select a better valve supplier, their valve might be more efficient, for example, has lower losses. That's not the case for you guys. It will all be the same. You'll all be using the same equipment with the same losses. So it's more about the overall system design to save cost. Any other questions about this table? Yep.
Let's say you don't know the parameters. If you put like just a valve into CFD, can
Yeah.
you extrapolate that from the data?
Definitely. Yeah, so this loss coefficient is something that, and this is how the manufacturers provide this too. So if you end up working in, say, valve manufacturing or some sort of shop that produces these components, you might be working on design to basically reduce KL. So if you measure the pressure drop across this valve in CFD or experiments, and you know the velocity and the density of the fluid, you could calculate the KL for your valve. And that's actually a really good question because later on we're going to see how some flow rate measurement equipment actually works under this principle. Any other questions about loss coefficient? I'm going to do an example now, so just so we see how to use this. So for example, compute delta P minor for flow at 0.1 cubic meters per second. Of water across a fully open 8 valve connected to NPS 12 schedule 40 pipe. So like I said, when we're doing our homework, we'll go look at this table. So I use the very specific terms fully open gate valve. So you know that I'm talking about the thing in this table that says gate valve fully open. So the loss coefficient there is 0.2. So by the way, this is how those control valves that I was talking about work. See how much the loss coefficient goes up as you're adjusting the amount that this valve is closed. Usually you don't use gate valves for flow control, but the butterfly valve is used for flow control. So the loss coefficient, the minor losses are much more convenient way to control the flow through our system, right? So if we were trying to use major losses to control the flow, every time we needed to control the flow, we'd have to like add or remove pipe. But once we put that valve there, we can just adjust its coefficient to control the flow. Anyways, so long story, KL is 0.2 based on this table. So KL 0.2. So we need to get the average velocity. In order to do that, we're going to do V dot over A. 0.1 over pi over 4, 0.303226 squared. I did some of these calculations last time, but this here, the internal diameter is given by the fact that we have NPS 12, schedule 40 pipe. So you'll notice this isn't the internal valve diameter. We don't actually need to know anything about the valve geometry. This is the pipe diameter, the D in the minor loss equation. Okay, so we have our V average now. Delta P equals KL rho V average squared. So that's 192 pascals. So that's just the minor loss from one valve. Any questions about that example? So now, I think where the minor loss stuff gets confusing is when we have a system that has multiple components in it. So system with multiple components that we need to calculate the total loss, major and minor for. So I'm going to do an example here. So I have an example picture of a piping system. Here. So this should be a fairly easy one to draw if you don't have if you can't copy and paste onto your notes. So I'll label some lengths here. So let's assume we want to calculate the pressure drop over what we can see in this picture. So let's take the total length of this to be 30 meters. I'm going to take the height here to be 5 meters. Can you see that okay? Okay, so we're going to assume the total horizontal length of this is 30 meters and the height is 5 meters. Yeah, Mike, do you have a question?
Why doesn't delta P matter or depend on like the initial pressure at all? I don't know why it would.
This is a pressure differential. Yeah. So it's the loss you get. It's like the kinetic energy change, say, by friction. Okay, in that case, that's probably a bad example because it probably does depend on that. Yeah, the pressure loss doesn't depend on the initial pressure. It sort of implicitly depends on that because if you have a higher flow rate, then you might have a different, if you pressurize the system a lot, you have a lot of flow rate, so then you'll have a lot of pressure loss. But for the same flow rate, it doesn't depend on the pressure at all. It's just a loss of, because remember, pressure is kind of a measure of potential energy. So this is just a loss of potential energy. No problem. Okay, so we're going to do an example now of calculating the total losses. So we're going to take this as the dimensions there. Let's take two 90-degree bends. We're going to take 0.1 as here, 0.2 is here. So the point of this question is to calculate total losses between 1 and 2. So let's assume we put a pump at 0.1 and the outlet or something like that is at 0.2. What pressure differential do we need to supply with our pump? Okay, so there's going to be a whole bunch of material properties and stuff I'm going to give. So D of 0.4, the average 3 meters per second, density of 1,000, mu of 8.9 times 10 to the negative 4. We'll take this as steel pipe that's been painted bright red for some reason. Okay. So the friction, okay, here, maybe I'll start with the minor losses. So the total KL between 1 and 2, we have two 90-degree bends. So we're going to do 2 times 0.3, 0.6. So that's our total minor loss coefficient between these 2 points. The 0.3 for that was actually for a flanged bend, but I'm just going to take that. The table doesn't have these welded, so these aren't flanges, these are welded. The table doesn't have for bends like that, so I'm just going to take it as flanged. Yep.
I was just wondering, do we assume that the two bends are far away enough that the pressure develops fully?
Yes, that's a good question. So the question is, this is a good question. So I said you put 0.2 far enough, say for the minor loss coefficient here, you put this point far enough down this tube so that the flow redevelops. So what if it hasn't redeveloped by the time it hits the next component? We don't worry about that in minor loss system analysis. In the real world, if you had a very critical part of your piping system that you were worried about the pressure drop for that, you can't do the analysis through these very loose kind of coefficients style stuff we're doing. So that's where you would probably use CFD. But it wouldn't be for, if you go to your boss in the real world and ask to do CFD for this, that's not a good look. Okay. So that would be for something like a really complicated flow component, or you're designing a valve, or you have like a bunch of valves and they're interacting and maybe they're creating a high velocity region that's spraying on one part of your tank so it could create extra wear, that sort of thing. Basically, anytime you're worried about the local flow properties, that's where this analysis breaks down, because there's a lot of, this is all about the average kind of velocities, average pressures. So our end goal here is delta P total is delta P major, delta P minor. That's F L over D, rho V average squared over 2. It's KL rho V average squared over 2. So we got our total loss coefficient. So in the interest of time and not making this feel rushed, I did major losses last lecture. So maybe consider it an additional exercise to verify that the friction factor for this works out to be 0.0132. So that's a constant friction factor along the entire pipe. The friction factor doesn't depend on the length of the pipe. Friction factor will change when we change our diameter. So our diameter influences our Reynolds number, it influences the flow rate, everything. So since the diameter is the same between points 1 and 2, we have the same friction factor. We don't have to break this up into additional smaller segments. So in this case, our delta P total, I'm going to move this down here, is going to be 0.0132. Our total length is what the major loss calculation has. So to get the total length of pipe, I will add up the horizontal lengths and the vertical length. So it's just 35 meters. So you don't worry about the fact that, well, it's not exactly 90 because it kind of bends through. That's accounted for in the minor loss calculations. So the total length is 30 plus 5 over the diameter. Plus our minor losses. Okay, so that's going to give us our total pressure drop. I'm going to factor this just so we can see. So I just factor this to, this is basically FL over D plus the total minor loss. And the magnitudes of these are 1.155 and 0.6. So this isn't that long of a section of pipe. So the minor losses are sort of comparable. They're still smaller than our major losses, but this isn't very long. So we have to account for minor losses, or we would underestimate the pressure loss through this. So the total here is 7.9 kilopascals. So are there any questions about that? The most confusing part is thinking, like, does the length have to go to the bend, and then we add the bend and then go the next straight length? You can simplify the analysis by just using the entire linear length of pipe if you just draw a line between those 2 points.
Can we make that assumption? Are we double counting the losses at those bends with the minor and the major?
You can you can think of the minor losses as accounting for the additional loss plus the sort of major loss of that length. So usually the length is so short for these components that I wouldn't say that's, yeah. So you can think of it that way. Yeah. Any other questions about this?
Yep. How do the magnitudes generally compare between the major and minor losses?
They're generally really small. So you can see here, like, this is a 30-meter section of pipe, so it's not very, very long. If we were to say double the length of this straight run, this L would, say we were to double, say we add an additional 30 meters onto that straight section, the length would double up to 65. So this would double here. So you already are like 4 times roughly higher on your major losses. And then when you have something going hundreds of meters, that's where the major losses start becoming major losses. Good question though. Any other questions? So that's why in the project, one of your deliverables is a table comparing the total major losses versus minor losses in your system. So maybe a hint is if you get your minor losses being bigger than your major losses, you've probably made a mistake in one of those calculations. Let's talk about head versus pressure loss now. So, okay, this should be called head versus pressure units. So if we divide a delta P by rho G, we get units of head, which is in meters. So the head loss major is delta P major divided by rho G. So that's F L over D, B average squared. over 2G. Same thing with the minor. So this is another unit system that's very commonly used in hydraulics. You'll see on Friday we're going to write a modified form of Bernoulli's equation in pressure form where the units are pascals. We're also going to write that in head form where the units are in meters. So this isn't really meters of any particular fluid, it's just meters head. So if you usually how this is given, for example, some pump curves will be given they won't be given in pressure units, they'll be given in head units. So you know that that's a given delta P for a certain fluid. So for example, a pump might get a different pressure differential if it's pumping oil versus water because they have different densities. Any questions about the head units? You'll become a little bit more comfortable working with those as we do some more system analysis. So on Friday is when we're going to really put lots of this stuff together, and you're going to see all these different terms of this modified Bernoulli's equation that we're building up are going to come together. So we'll talk about flow rate measurement. Sorry, before I move on, are there any more questions about the head form versus? So you'll notice in the head loss form, if I asked you to calculate the head loss for a valve, you don't need to know the density of the fluid anymore. All you need to know is the velocity of flow through the valve. Because remember, this delta P minor, if I ask you to calculate the pressure loss for the valve, that's where you need density. Any questions? So has anyone on a co-op term or in your own experience came across, so let's say we have a pipe running through this room and we know there's some fluid going through it and you're not allowed to do the water bucket technique. I don't know if you've done that in any labs where you measure the volume of water going into a bucket over a given period of time. Let's say you're in a plant somewhere and there's a pipe there, and obviously the pipe is opaque because it's made out of steel or something. How do you measure the flow rate? How is it done in the real world? The flow rate through a pipe. Does anyone know any pressure measurement equipment or devices for that? Look at the drawings. So that maybe is the nominal case. When you're controlling this, yep. A strain on different parts of the pipe. That's an interesting one. Yeah, so that could maybe give you the pressure if you had a very good, yeah, so that could give you pressure. Yep. I think that might actually be used for pressure measurements in some very like niche cases. Normally pressure would just be measured with like a static pressure tap that we stick a valve on. So any other? No? Yep.
Can I like a flow meter between two pipes?
Okay. Yeah, flow meter. That's fair. We measure flow using a flow meter. So I guess, does anyone know like a working concept of any flow meters? There's an inline, that's the type of flow meter. Yeah, so inline it's in line with the pipe. So the flow has to flow through this flow meter. Okay. I guess, maybe that's why you're here, to learn about flow rate measurement. So let's talk about two of the most common types of flow rate measurement in industry. So the common technique is to measure delta P across a well-characterized component. So remember, our delta P is KL rho V average squared over 2. So if we know KL, and we measure that delta P, we can calculate the average. So in principle, this could be done on something even like a valve. You know the KL of your valve. You measure the pressure at the start of the valve and then the pressure kind of after it's recovered, far downstream. You could calculate the velocity of this fluid. It's not usually done with valves in practice. It's done with more special type of components. So there's two examples that I'll talk about. So the first one is an orifice plate. And that is, it's literally just a plate you stick in the pipe. So say you have a pipe like this. You put, so that's kind of a side view, but the front view is it's just a plate with a hole in the middle of it that you stick in the pipe, and then you measure the pressure here and here. So the pipe has some diameter d, the orifice plate has a smaller diameter d there. This is different than the minor loss that I talked about. That pressure drop there, delta P, is not the same delta P of the overall minor loss of this orifice plate. This is how the measurement works, because in practice it's pretty impractical to measure the pressure differential across that. So you can just put two pressure taps like literally right beside each other on each side of this plate. And the equation is a little bit different, but it's the same principle. So this is not the same thing as the unrecoverable minor loss. There's also something called a Venturi. It's the exact same principle, but overall the efficiency is much higher. So you measure the pressure. I'm going to just indicate exactly how the pressure would be measured. So you would have some sort of pressure tap here. So they use the exact same principle. They measure a pressure drop due to a, I guess they measure a pressure differential. But the Venturi has a much lower minor loss because the expansion and contraction is much more gradual. That being said, Venturi flow meters are much more expensive and they take up a huge amount of space. So an orifice plate is a very thin plate. You can just stick it right in your, like in between, say, a flange. That's usually how it's attached. It takes up almost no space, but you pay a penalty for the minor losses. So in components where maybe it's not that expensive to add additional pressure to the fluid, so like some steam supplies and like refineries, they'll use orifice plates for flow measurement. You would use, yeah, orifice plate there. But for like a pipeline that moves liquid across the country, they don't use orifice plates for that. One, because the velocity is so high, these things wear out. And two, because it's, like I said, a major cost is providing pressure for those. So here's the equation that's used to calculate the volumetric flow rate through one of these devices. Volumetric flow rate is A0 CD for 2 P1 minus P2 over rho 1 minus beta to the 4. So A0 is our orifice plate or our restriction diameter. And beta is the ratio of our diameters of our restriction to our nominal pipe diameter. CD is our, it's called the discharge coefficient. And it's not equal to the minor loss coefficient, but it's really a similar idea. So the CD for real devices is highly, it's Reynolds number independent, Reynolds number dependent. And geometry dependent. So by geometry, I mean it depends on beta and Reynolds number. So in practice, when these are used, these are very well characterized in terms of Reynolds number, geometry. But in this course, we're just going to assume that a constant CD of 0.61 for the orifice plate and 0.98 for the venturi. Okay. So that, like I said, the discharge coefficient isn't the same as the loss coefficient. You can see the venturi, the discharge coefficient of 1 is perfect flow, so you're not losing any energy through it. And the venturi is quite good at 0.98. Orifice plate is pretty bad at 0.61. But in some situations, you don't really care that much. Yep. There.
D diameter is like here, the small one is.
Yeah, capital D is out here. So venturi flow meter, so is basically, so it goes after the venturi, it goes back up to diameter D. The venturi flow meter is this whole device here. So they're very long. We're not going to really talk about them that much in this course, but like I mentioned, for pipelines that transport flow very far, for water mains that transfer, I'm not sure if they're used for water mains, but I know they're used for pipelines. They use ultrasonic flow meters. So that's like an inline flow meter with almost no pressure drop. So it uses the Doppler effect actually to measure the flow rate. That's definitely beyond the scope of Fluids 1. There's also things called rotometers, which is a small spinning thing in your flow. Accurate flow rate measurement is super important. We have to know like how fast the flow is going through our pipe for many different reasons for the control system. The people who charge you for gas have to know how much gas to charge you for. If you're, I guess, working at a plant, you have to know how much money you're making. So that's why we have to measure flow rate. Yep.
Gas station, like it might a little thing, but would you not for a lot of these things, if this matters for how much stuff you're losing, you just take the mass you had before and mass after?
See, I think for a gas station, it's all coming from the same tank, right? So there's multiple people pumping at once, so it might be hard to figure out. So I think the gas, I'll look this up to let you know next lecture, but I think the thing that measures how much gas to charge you for is in the pump itself. So it measures the flow going through there. Yep.
For financial purposes, could you slow the rotometer down by having a magnet next to it?
For financial purposes, I wouldn't say that's fun. I would say that's fraud. Yeah, so don't listen to that. I'm going to play now an animation of the orifice plates. So I don't have time to show this whole video. One more thing. So I don't have time to show this whole video, but I'll post it on Learn because the CGI in this, I don't know why this company went so hard on the CGI for their.
Here's how this
It's like
method
Dune
works.
level. I'm not even.
Differential pressure flow
So
meters
anyways,
have an artificial restriction.
so this is an
integrated
orifice plate. You
into
can
the
see it's a
measurement
really small. It's a really small device, right? This whole thing
This
is
measurement
just
method
in this
works.
little flange, and there's a differential pressure gauge
flow
here
meters have an
with pressure
artificial
taps going on
restriction
each side of the
integrated
orifice
into
plate.
the measuring tube.
So this is a very common
illustrated
type of
here
flow
by the
measurement
example
device.
of an
The
orifice
pressure is
plate.
measured directly. That discharge
holes are
coefficient
located
is
in the pipe
calibrated
wall,
for the pressure measurement
one
here.
before
So this
and
is
one
all
after the orifice
well
plate.
characterized by
Two separate tubes connect these
but I do
holes
recommend
to a
watching this because they also
differential
do
pressure sensor
the
with its
venturi
two
in this
pressure
video.
chambers separated by a diaphragm.
Any other
The
questions?
tiniest pressure differences in the flowing.
Any other questions here? That's to measure the pressure differential. So this diaphragm is how some types of differential pressure sensors work. Any other questions?